Based on what we've done in previous lessons, we could find the area in between two curves, or area bounded by two curves. We use the top minus bottom and use the definite integral of that to find the area. Now, that doesn't always work, and this is a perfect example of when it might not work to use the top curve minus the bottom curve. If you look at the area bounded by these two curves, it's this crazy shape here. Now we can find the area of that shape, but you should agree that the top curve minus the bottom curve doesn't always work, because, for example, take a look here. If I'm trying to integrate from this value A to this value B with top curve minus bottom curve, our top curve and bottom curve change. This curve, if it was top minus bottom, it's the same curve. This is a parabola that opens to the right. So we don't have a definite top curve and bottom curve, a function f of x and g of x in this case. Now, could we write equations to model each of these things separately, kind of as a piecewise function, and find the area? Yes, but that always isn't the easiest way to find this area. So what you're going to be learning in this lesson is how we can find area of curves that are not necessarily always top minus bottom. Okay, so when we run into a problem where we have to find area between two curves, where top minus bottom doesn't necessarily work, there are other options for us to consider. And this kind of introduces us integrating with respect to y. When you have two curves that are better defined by a right curve and a left curve, we can integrate with respect to the y values, or the y-axis, which will make our rectangles that we're using to approximate horizontal. So we're kind of integrating horizontally other than vertically. So this we will integrate with respect to the y-axis, and you can see that we'll want to do this whenever you have a curve that is defined on the right and the left. So that will bring us to the actual formula to integrate with respect to y in order to find the area between the two curves. Now this, if I think about it rotating, it's still kind of like a top curve minus a bottom curve. We're going to use the same idea. So we're now going to integrate from C to D, and those will actually be y values. So we have a lower limit C and an upper limit D. So the area between two curves, if I have a curve that is described, the x values are in terms of y, which is a little different than you're probably used to. But the area between the two will be given by the definite integral from C to D, lower limit, upper limit, of this curve, the right side, f of y, minus the left side, g of y. And now you can see that we have a dy. This formula here will give us the area between two curves. We just have to write our equations so that they say x equals some function of y. And you can see, based on our previous lesson, we said that we would do top minus bottom inside the definite integral. When you have a right and a left curve, it will every time be right minus left. So if the previous lesson we want to remember is top minus bottom, today right minus left. If you know that, we will be able to integrate with respect to y. Taking a look at example 4 on the notes. We're given two curves, and you may remember this one from the previous video when we were doing top minus bottom. We had to do a lot of geometry to find the value, and we subtracted out the area of this triangle to find the shaded region. Where really this area of this shaded region is better off to integrate with respect to y, since I'm given a line or a curve that is on the right side and another that is always to the left of it. Using those two things, we can integrate with respect to y in this case, and it will be much easier than trying to add and subtract all these crazy geometry things to find the area here. So doing so, first thing we need to do is write both curves in terms of x. Sorry, in terms of y. So it needs to say x equals. So this curve, it is y equals x minus 2. We need it to be x equals, so it needs to be in terms of y so we can integrate with respect to y. So this would be x is equal to y plus 2. Our other curve, y equals the square root of x. This, if I solve for x, would be x is equal to y squared. Now that's a little different than you're so used to as far as our ordered pairs and our x and our y's. We're going to basically be inputting a y and finding an x. So for example, if I want to find this point on that curve, I know the x-coordinate is given by the y squared. Well, our y value is 2. I can plug that y value in, 2 squared, our x is 4, and you can see that the ordered pair, when y is 2, x is 4. Very similar to what you've done, we're just inputting y values instead of x values. Okay, with that said, now we can integrate with respect to y. So we're going to write our integral similar to the way you've done it all along. The only difference is we're going to have an upper and lower limit that are y values. Our lower limit for the area of that shaded region is the y value 0. And the upper limit for that shaded region is the y value 2. So you can tell that the area under this curve is the definite integral from 0 to 2. Now we want to use right curve minus left curve every single time. Remember that right minus left, right minus left. So the right curve is this line, y plus 2, minus the left curve, which is y squared. And it is dy. With this, we can simplify inside if you wish, and then we will go ahead and use the fundamental theorem of calculus to evaluate this definite integral. So, doing so, we see that this is equal to our antiderivatives. The antiderivative of y is y squared over 2. The antiderivative of 2 is a positive 2y. And the antiderivative of this is y cubed over 3, and all of that is evaluated from 0 to 2. Now, using fundamental theorem of calculus, you can evaluate that, and we will have 2 squared 4, 4 over 2 is 2 plus 4 minus 8/3. Subtract, that would be 0 plus 0 minus 0. It's a tough one for you. And simplifying here, we have 6 minus 8/3, which is 10/3. And that is units squared. Simple, as long as you understand our definite integrals previously, and as long as you can solve the original equation in terms of y. We can find the area in between these two curves or bounded by these two curves using your new integration with respect to y. Now, a couple of things you need to know. We need to find lower limits and upper limits. And we also need our equations in terms of y. So with that being said, our lower limit on the y-axis is going to be this value. It is that value where we start to integrate or find the area between the two curves. The other value, or our upper limit of integration, is going to be at about that point. So it looks to be about -1 for the lower limit and just less than 2 for the upper limit. That is where we will be integrating with respect to y. So we need to find those values. And first thing I would do is go ahead and write our equations in terms of x. So this first equation you should have as the cube root of y. And the other equation is already given in terms of x. So it's x equals y squared minus 2. There's our two equations in terms of y. So we have a right curve and a left curve. We can start our integral. We know that the area between the two is going to be some definite interval. We'll find the upper and lower limits here in just a second on the calculator. Of the right curve, which is the cubic, it would be this one, cube root of y, minus the left curve, which is this parabola opening to the right, y squared minus 2. And that's integrated with our dy. Now we need our upper and lower limits. Let's just verify a couple of things. For the calculator, you can see that I entered in the y equals, I have x cubed, that's our original curve, this cubic here. And the other curve, if I solve it for y to type it in the calculator, it would end up being plus or minus square root of x plus 2. So if I solve that for y, so I can enter that in the calculator by doing a positive square root of x plus 2 and a negative square root of x plus 2, which gives us our graph here. Now, finding the values, we need to find this intersection and look for the y value, so I can do second calculate, intersection, first curve, and second curve. Now this is the positive square root. I want it to be on the negative square root. And you can see now by hitting the up arrow, I'm on the negative square root, and then it says guess, we'll get it close. And you can see that the intersection is 1, 1, or negative 1, negative 1, sorry. So this point is negative 1, negative 1. On the y-axis, our lower limit is negative 1. Now we need to find the upper value. We will do second calculate, intersection. Our first curve is the cubic, second curve is the quadratic, and we can guess by just getting it close. And we come up with a value that is 1.21 on the x, but we're looking for the y coordinate, 1.793. It's a decimal approximation, so just as we did previously, you want to store that in the calculator, 1.7930037. So, the easiest way, since it's a y coordinate, is we will write that down and store it. So it is 1.7930037. I'm going to go to the home screen and store that. So we want to store 1.7930037. And I'm going to store that in alpha d. That is our upper limit. So we are going to be integrating up to the value d. So we will say that d is approximately this decimal. That way we don't have any rounding errors when we finish. Alright, now the easy part. We can type this in the calculator and let the calculator give us the value. So our integral, we will, if we want to do it on the home screen, go ahead and go to Math, and down to the bottom, number 9, just like the previous lesson, we will type in our values, which is the cube root of our variable. Now this is a y, but it's a variable. You can type an x in and the calculator will give us the right value. Minus, and I'm going to put it in parentheses, it's x squared minus 2. And then you hit a comma, and we are integrating with respect to y, but the calculator doesn't know x's and y's, so you have to put an x here. Wherever there's a variable, we're just basically putting an x. And our lower limit of integration is -1. Our upper limit is stored in alpha d, or the letter d. And when you hit enter on that, The calculator will think for a minute and come up with our value. It should be somewhere around, at least from my previous work, perfect. This is about equal to 4.215 units squared. Okay, for the next example, we're given two curves and we need to decide whether we want to integrate with respect to x or with respect to y. So basically, do we have a top curve and a bottom curve, or do we have a curve on the right and a curve on the left? That's what we're trying to ask ourselves. So when we do that, the first thing I would do is try to think about or even sketch the graph if you can. If it's calculator active, go ahead and graph it in the calculator. To graph it in the calculator, you have to have them in y equals, and a lot of times to think about it in our brain, since we're so used to it, it's easy to put them in y equals. So this curve is y equals negative x plus 1. We know that's linear, negative slope, y-intercept of positive 1. And the next one we have is, it would be x over 2, and that would be a plus or minus square root. Okay, so that is solving both of them for y to get an idea of what the curve is. Now, if I'm going to sketch these things, here is my axis that we're going to sketch on. This curve is easy to sketch. I know what that one looks like. Like I said, it has a y-intercept of 1. And a slope of negative 1. That means we go down 1 over 1. Alright, so there is one of our curves. Simple. This one is a little bit more challenging to think of, and you can even graph points given y values. For example, if I plug in a y value of 1, my x value is 1 squared is 1 multiplied by 2. My x is 2. So an ordered pair for this equation, when y is 1, my x is 2. So it is 2, 1. And that is one of our values on the curve. When our y value is 0, we could plug 0 in here, our x is 0. When our y value is negative 1, we can plug it in here and come up with an x value of 2. Negative 1 on the y and 2 on the x. I'm going to take this and make our window just a little bigger here. This is what our curve is going to look like. Just like this. And that gives us our shaded area, which will be that area. With this basic sketch, we can easily determine what we want to integrate with respect to. We have a right curve and a left curve, which tells me instantly that we want to integrate with respect to y. So we are going to integrate with respect to y. So I want my curves in terms of y. So this would be x equals 1 minus y. And this one is already in terms of x, which is fantastic. Alright, so our two curves. We can easily find the area of this. We know that we're going to have the area equal to our upper and lower limits of integration we'll find here in just a second. But we know that we're going to do the right curve, which is this one, 1 minus y, minus the left curve, which is this one, 2y squared. And all of that is what we will integrate with respect to y. We need an upper and a lower limit. A couple of ways that we can do that. I would say the easiest way is to set these equal algebraically and then solve. If it's calculator active, once again, you can type them in the calculator and go ahead and use your variables for your upper and lower limits of integration. If we find these ordered pairs, you can find them very easily, like I said, by setting them equal, and you'll find that that point is 1/2, 1/2. And this point, which is our lower limit of integration, is actually 2, -1. So we have an upper and lower limit of integration of -1/2. Or -1 and 1/2. Now this we can simplify easily using our knowledge of definite integrals. I'm going to simplify it inside just a little bit to make it a little easier to read. So this is a -2y squared and a -y and a +1 integrating with respect to y. Solving. Antiderivatives. Antiderivative of this, we would have a -2y cubed over 3 minus a y squared over 2 plus a y, and all of that is integrated from -1 to 1/2. Once you simplify this using the fundamental theorem of calculus, we will have the actual area between the curves. That should be relatively easy for you at this point. Even if it's not calculator active, you can go through and do that algebra very easily. You should, when you do that, come up with an area of 9/8 units squared. For the last example that we have today, we have find a horizontal line y equals k that divides the area between x squared and 9 into 2 equal parts. So here is the infamous y equals k, or bringing in this crazy constant that we see so often in calculus, k. Before we do anything, I'm going to go ahead and sketch what this looks like, and then we'll kind of dive into what the problem is actually asking. Here is our line y equals k. And here is our line y equals x squared. It's not a line, it's actually a curve in this case. It should be a beautiful parabola. Mine is not quite beautiful, but you're just going to have to accept that. We know at 3 our value is 9, and at -3 our value is 9. Now, what we're looking for is some horizontal line y equals k that divides the area between these two things directly in half. It is a horizontal line. So the line we're looking for is this line here. Now, there's a y value, a k value, somewhere in here that makes it so that the top part, its area, is exactly equal to the bottom part's area. Obviously it's not this high, and obviously it's not this low. There's somewhere in here we have an area where they're equal. That is the k value we're looking for. So this is the line y equals k. Now, a couple of things that we need. First, we need to know this total area here before we even get into the line y equals k. That total area you can find very easily by our area integration. So from -3 to 3, and we're integrating with respect to x in this case, the top curve, which is 9, minus the bottom curve, which is x squared. And that is a dx. Now that will be easy for you to integrate and evaluate. The answer is 36. This area here, enclosed by the line y equals 9 and the line y equals x squared, has an area of 36 square units. So, what we're looking for is some area so that these two things are equal in area, which means If it's 36, that means 18 square units need to be above the line, and 18 square units need to be below the line. We're going to need to deal with some sort of integrals, and that's what we'll set up, and we'll use an upper and lower limit that will be kind of tricky. So, first thing that we're going to do, you should agree that this is an even function. So I know that 2 times this area will equal the total. So I'm going to end up using an integral multiplied by 2, and we're only really going to deal with this right-hand side. Now, we know that we have some top curve. This is the line y equals k. So we know that we have a top curve in this case. If I'm finding the area of this bottom part, I want it to be equal to 18. That way it's 18 here and 18 at the top. We know that that line is y equals k. So this value has an ordered pair with a y value of k. That's going to become very important because now we need to find the x value, because that is the value that we will actually integrate up to. Our upper limit will be an actual variable in this case. Well, k, it's a constant, but you'll see how this is going to work. If my y value is k on this curve, using our equation, our y is k. So that means k is equal to x squared. Now, to find our x coordinate that we're going to have as an upper limit of integration, it is, if k is equal to x squared, then x must be the square root of k. So this value here that we're going to integrate up to, our upper limit from 0 to the square root of k of the top curve, which in this case, the top is this curve. We don't know what that number is, but we know that number is k. Minus the bottom curve, which is x squared. Get this out of the way here. And that will be a dx. That should be equal to half of our area. We want it to be equal to 18. Alright, now all we're going to have to do is simplify this and solve for that variable k. So using our antiderivatives in the fundamental theorem of calculus, 2 multiplied by this antiderivative of k. Remember, k is actually a number. The antiderivative of that would be kx minus x cubed over 3. And that is evaluated from 0 to the square root of k. And that should be equal to 18. So, fundamental theorem of calculus, I still have my 2, but we know that we can divide that 2. So this, kx minus x cubed over 3, evaluated from 0 to the square root of k, is equal to 9. Solving, using the fundamental theorem of calculus, substitute this in for x. It would be k square root of k minus square root of k cubed over 3 equals 9. Now we have it all in terms of k. We need to now solve for that k. And one quick thing, I left off substituting in 0 because that would cancel out and make this 0, and it would cancel out and make this 0. So just so you know that I didn't forget that, this is going to be 0, so we don't have to subtract 0. Now, solving this, we can go ahead and do. Using your algebra, we will solve. So the cubing the square root of k, that's the same thing as square root of k multiplied by square root of k multiplied by square root of k, which you know is square root of k multiplied by the square root of k is simply k, and we still have another square root of k. So it's k square root of k minus k square root of k over 3 equals 9. Simplify. Multiply each of these by 3. so that we have a common denominator. Now we can subtract. 3k square root of k minus 1k square root of k is 2k square root of k over 3 equals 9. Simplifying further, multiply both sides by 3. 2k square root of k equals 27. This k square root of k equals, divide by 2, 27 over 2. Use your exponent properties. Square root of k is the same thing as k to the 1/2 power, which is k, add exponents to the 3/2. And now simplifying, this is the square root of k cubed equals 27. So we can take the square root, so this is the square root of k cubed equals 27 over 2. So k cubed equals 27 over 2 squared. And then it's the cube root of that. So k is equal to 27 over 2 squared. And it's, let me fix that. The cube root of 27 over 2 squared. That is our k value. And if you go ahead and type that into a calculator, you're going to get a k value of approximately, it is 5.670. That is our k value that makes the area, make sure you have that number, 5.670. This y equals 5.670 is that value of the line that cuts this area exactly in half. This area with this line 5.670, there is 18 square units above the line and 18 square units below the line, giving a total area of 36, which was our original. That one is tricky. You may need to pause, rewind, pause, rewind, pause, rewind. But I'm sure that after a couple times of seeing it, and we'll work on some more in class, that you'll be able to find a value of k in any instance of these type of problems. That is all. Reviewing very quickly. If we have a curve that is on the right, a curve that is on the left, we can integrate with respect to y and do right minus left. Very similar to top minus bottom, same concept. Just make sure when you are putting your integrals in, you have them with an x equals if we're going to integrate with respect to y. Y is now our variable. Other than that, it works very, very similar.